In this video, I want to talk more about nth roots, formally defining them, and expanding towards how we write different roots as rational or fractional exponents. So, the definition of what we call a principal nth root of a number is written above, but it's basically the same idea as a square root or a cube root, the key idea that we've already been discussing in previous lectures. But like, for example, if say for example, I want to know, well, what's the square root of 4? As I described before, well, technically 4 has 2 square roots, and to find a square root, we're looking for, well, what number squared makes 4? So we'd say that 2 is the square root of 4, or in, a definitive sense, it would be a solution R to an equation to which, when squared, it would produce 4. And so kind of looking at the definition of the cube root as phrased right here, it says that R is equal to the cube root of A would represent a number which satisfies A is equal to R cubed. So in that sort of way, in this, in a similar sense, 2 cubed, we'd say that that is the cube root of 8, because 2 is a number which cubed produces 8. And it's always symbolized by the nth root of A by using the radical symbol. And that applies to all forms of roots. When we use a higher index, that just shifts the exponent on our connection there. And I gave a couple other examples, like how 27 is the cube root of 3 because 3 cubed is 27. And same with 32. The fifth root of 32 is 2 because 2 to the fifth is 32. So that's kind of the logic. We're always looking for, well, how many, what number raised to the fifth power makes 32, if anything. And of course, if it's nothing logical, it often would be in the form of an irrational number. And as we discussed before, when it comes to cube roots or odd-powered roots, we can have an odd power nth root of a negative number and it will work. Like, the cube root of negative 64 is negative 4, because if you take negative 4 to the third power, it would make a negative. So, looking at some other cube roots, as in the packet, cube root of 1000, well, a thing with zeros is you can count the number of tens in a number by seeing how many zeros it has. So 1000 is just 10 times 10 times 10, meaning it's 10 cubed. So if I was to try to figure out, well, what's the cube root of 1000, that would just be 10. And again, I could kind of think about that like this. 10 to the third power is equal to 1000. And that's a synonymous form of the meaning of a cube root. And that's all that arrow means, is that if this is true, then this is also true, and vice versa. If this is true, they're both simultaneously true, an equivalency statement between the two forms. And with the cube root of a negative number, the thing about the actual numerical component is the cube root of the negative will basically pass through the cube root, or it won't do anything. So, since I already know that the cube root of 1000 is 10, the cube root of negative 1000 must be negative 10, because negative 10 cubed makes negative 1000. But when we're talking about even-powered nth roots, I could be looking for, well, what number to the fourth power makes 256, and you could always hazard a guess as to what that might be. But as I said in the in the last couple videos, you could also use a calculator to find the principal nth root of a number. And again, we call it the principal root just because there are technically more than one. Like with the square root of 4, there's technically 2 square roots of 4. But since it's a function, we only want one answer, which is why we only give the positive side of the story. But you could always check the principal nth root of a number with the calculator, and I could see, okay, well, yes, the principal fourth root of 256 is 4, because 4 times 4 times 4 times 4, 4 fours makes 256, and that checks out. But with the fourth root of a negative number, as we said before, since no real number raised to the fourth power can make 256, because if it's multiplied 4 times, it must always become a positive outcome. And basically, you could check in your calculator, but I wanted to show you what it would return if you were to type that in. We would need to type in the fourth root of negative 256, and that would give us an error, non-real answer. So this is your calculator will recognize, okay, this gives me an error because that number is not within the domain. If it's not within the domain, then we don't use it. But technically, as we're going to talk about, there are technically answers to this. Every number has always nth roots to it. But when it comes to the principal root, it's always positive, and we're always looking for a real value for that solution. Now, the cancellation principles of roots are another thing that is a little bit of a strange property, where what happens if I take the root of a perfect square? Like, looking at some of these, like, say for example I was to look at the cube root of 1000, I could have rewritten that as the cube root of 10 cubed, because 1000 was equal to 10 cubed. And what we could conclude from that is that the cube root cancels out with the cube, and just like how a square root cancels a square. And this is the nature of what we call mathematical inverses, or inverse functions, and this is something that we'll discuss later. But basically, we call them the cancellation principles, because when we apply an nth root to the particular nth power, they will cancel each other out as such. Well, in certain circumstances, it actually works a little bit differently than that. So if you look at the cancellation property, notice that basically this thing where I canceled out the cube root with the cube is highlighted by this principle here, which is that the cube root of x cubed is just x. And that's a true property. And you might notice that for every odd indexed root, the nth root will cancel out with the nth power and leave us with just x. So looking at a particular example, let's say I wanted to do what's the cube root of -2 cubed. Well, I could just evaluate -2 cubed, because -2 cubed is -8. But the cube root of a cube is just the base number -2 because of cancellation. And I mean, you could confirm that just by doing the math. And same with the fifth root of -2 to the fifth. That would cancel itself out and produce -2 as well. Because -2 to the fifth would just be -32, and the fifth root of -32 would be -2, obviously. So the thing about this is that however, whenever the power is an even number, it doesn't quite work the same way. Because technically, one of the things we talk about is, well, when you have a negative number on the inside, it doesn't work because it produces a non-real answer. But notice that if I phrase it as a -2 squared, that's really just a square root of 4, which is just a +2. But what you want to notice about this is that when you're taking the square root of something squared, it always produces a positive outcome. It only gives us the positive answer. And so that's why above the cancellation property, when I take the square root of x squared, it's not just x, it's actually the absolute value of x, because the principal square root only returns a positive value. And remember how I said, well, technically -2 is also a root of a number, but since the radical symbol only returns a positive answer, that's why it doesn't cancel exactly correctly. And there is merit to the sense behind taking it, canceling, and just making -2, obviously, because -2 is a root of 4. But since the square root sign returns a principal root, basically a negative sign gets canceled or absorbed in this process. And what this implies towards equations is equations of this nature actually have two different solutions based on both plus or minus. And the same thing is applied to the fourth root of -4, is the fourth root of something to the fourth power is the absolute value of x. Because again, if I was to evaluate the interior here, well, -2 times -2 is 4, times -2 is -8, times -2 is 16. So this would make the fourth root of 16, which is of course a positive 2 in the same way. So notice that the absolute value is being applied to it, and that's kind of the reason why. What I just recommend remembering is that if you're trying to solve an equation by using these cancellation properties, and we're going to get to that in a few sections, you need to remember that when you take the square root of something squared, it actually produces an absolute value. It's not obvious, but that's kind of the reason I wanted to look at that in this particular video. That'll wrap this one up. In the next video, we'll be talking about rational exponents, fractions, those definitions, and kind of expanding this to other forms of other ways of writing roots.